All right, in this video, we're going to talk about approximating a function using a tangent plane. Now, you guys have done this before, but with tangent lines in Calc 1. So let's kind of go over that so you can remember that just a bit. So in Calc 1, if we had some function, so there's our function of x, at any point, so let's just say at this point A, we could, axes in here, we could from point A, we could go up to the graph and then over, and we could find the value of the function at A. Now, because of calculators and stuff, this is easy, but back in the day before there was calculators, it wasn't so easy. And so there were some times when we had functions like square roots or exponentials that it might be nice to actually use the tangent line. So we could come up here, we could find a derivative, which would be the slope of our tangent line. And then if we wanted to calculate a different value, so let's say that now we actually are considering calculating a value at A plus some bit away from A. So the actual value there of the function would be somewhere up in here. We would find the actual value of the function at A plus delta x, if that were possible. But if it's not possible, then we could find the tangent line, and then we could use the tangent line. So at that value, that new value, we would go up to the tangent line, and because it's linear, the calculation is often doable by hand if the other one was not. So this would be our approximation for that function, our approximate y value. And then let's see, some other wording in here. So the difference between, let me pick another color here. The difference between the point where we would start at, so the difference between the A and the function of A, and then the approximate value, and it's the approximate value because we're using the tangent line, that we refer to as dy, and it's called the differential. So that differential is the change in height, taking the tangent line into consideration. All right. Okay, so what I'm going to do now is I'm going to kind of put a formula together for you for the tangent plane. Now, remember that an equation of a plane in general looks like A times x minus x naught plus b, some value b, times y minus y naught, plus c times z minus z naught is equal to 0. If I solve for z minus z naught, I would have to subtract over a, divide it by c, that would be multiplied by x minus x naught, and I'd have to subtract over b, divide it by c, and that would be multiplied by y minus y naught. So then let me just rewrite this. Because a divided by c and the negative of that, it's just some number. I'm going to call that little a. And the same with negative b over c, it's just some number. I'm going to call that little b. Now, if I set y equal to y naught, so if I set y equal to a constant, then what I get is z minus z naught equal to a times x minus x naught. And so essentially what this is, we kept y constant, and so this would be a line with a slope, because y is constant, it's with a slope of a partial derivative of the function with respect to x. And if I do the same thing with x, so if I keep x constant, then if I'm considering slope, it would be a partial of f with respect to y. But if I keep x constant with this equation of the plane, I get z minus z naught is equal to b times y minus y naught. Now here's a different line. And this one now has a slope of the partial of f with respect to y. So now if I use the fact that a is going to be this partial of f with respect to x, since that is the slope of that first line, and b is going to be the partial of f with respect to y because that's the slope of the second line, then what I get out of this is that z minus z naught is going to equal the partial of f with respect to x. Now we need to evaluate this, so it'll be evaluated at some point x naught, y naught, times x minus x naught, plus the partial of f with respect to y, that should be evaluated at the point x naught, y naught, times y minus y naught. There is our equation of the tangent plane. So there's our equation of the tangent plane. So to find it, we need to find the partials of f with respect to x and with respect to y, plug in the point that we're trying to find the tangent plane at, and then basically plug and chug through the formula. Now, if we wanted to now use this tangent plane, we can approximate a z value by just solving for z. And what this is called is a linear approximation, and so this would be the linearization. So if we solve for z, a lot of times this is written out as like an L, like just using L, it'd be a function of x and y. The linearization is going to be, all I need to do is solve for z, that's bringing z naught over to the other side of this tangent plane equation. So I'm just kind of rewriting the tangent plane equation here when I brought over that z naught to the other side. So if I could not find a z value easily given whatever function I'm given, I could instead find the tangent plane, solve for z, and then use that z to then approximate the value that I was looking for. I've imported this photo so that we can get a visualization of what the tangent plane and a linear approximation would do. So this picture kind of shows the tangent plane, and it shows the tangent plane at a point kind of maybe like from right there. Now, say we were looking to find we want a z value when, say, let's do x is equal to 2. So maybe not when here, but at when x is equal to 2 and when y is equal to -2. That looks like a pretty good point to me. So if we go about 2 and x, -2 and y, that puts us on this shape right about there. So from the graph of it, and because we have a graph, we can come over here and we can say that here is our z value from that point. So the z value, the actual value of it is going to be about, I don't know, what's that, about -15, say, is the actual value. But if we had some function where it was really difficult to plug into a -2 and calculate it, and I'm talking about by hand, if we find this tangent plane, then what we would do is go to that point, that same exact point at 2, -2, but this time we'll go up to the tangent plane at 2, -2, and we'll use that. And if we use that, then that would give us our estimated or our approximate value for z. So in this case, the approximate value, if I did 2, -2, would be, 18? That looks like it's a pretty big difference there. And I think it's a really big difference because I'm choosing a point kind of far away from this point from the tangent plane. From this point, there we go. From the point that the tangent plane was found from, because the point that we're looking for the z value at is far away from that, we get a pretty bad estimate of it. If we chose something closer, we would get a better estimate. All right, so now let me show you how to do this in practice. Okay, so now for an example. Let's take our function and let's look at the function square root of 2x plus y. And first thing let's find the tangent plane at the point 2, 5. Now I'm going to write up here in the corner so that we can remember it. I'm going to write down that equation for tangent plane. So on the page, a couple pages ago, you saw that the tangent plane is z minus z naught times the partial with respect to x at x naught y naught times x minus x naught plus the partial with respect to y at x naught y naught times y minus y naught. Okay, so what we're going to have to calculate in all of this, z is going to stay as z. We're going to need to calculate a z naught. We're going to have to find the partial with respect to x at x naught y naught. And we're going to have to find, let's see, x naught is given, and we're going to have to find the partial with respect to y at x naught y naught, and y naught is given. X naught and y naught, I just said they were given because they're right here. There's x naught, it's 2, and there's y naught, that's 5. That's our starting values for x and y. All right, so we need to find z naught. Z naught is going to come from our function evaluated at that point, 2, 5. So if we plug in 2, 5 into this function, 2 times 2 is 4, add 5, we get 9. Square root of 9 is 3. So there's that one. Then we need to find the partial with respect to x. So now if I take the derivative of that function with respect to x, I get a 2 in the denominator, square root of 2x plus y in the denominator. And in the numerator, I'm going to have to multiply it by 2 because of that 2 in front of x. Now I need to plug in 2 and 5. I can cancel those 2's. And we just said that the square root of 2x plus y when I plug in 2 and 5 was 3, so I get 1/3 for that partial of f with respect to x. Now I've got to find the partial of f with respect to y. So that is going to be, let's see, we'll have the 2 and then that root of 2x plus y in the denominator. This time just a 1 in the numerator because there's a 1 out in front of y. That root when we plug in 2 and 5 was 3. 3 times 2 is 6. So the partial with respect to y is 1/6. So now all I need to do is plug all of these into that formula. Z stays as z minus z naught, which we calculated as 3, is equal to the partial of f with respect to x at x naught y naught, that's 1/3, times x stays as x minus x naught, which was 2, plus the partial of f with respect to y at x naught y naught, that's 1/6, times y minus y naught, which is 5. There's our tangent plane. Okay, now let's find the linearization. So the linearization is the linear approximation in this case, we're using a tangent plane to approximate a z-value. Now, because we're approximating the z-value, that linearization happens, well, it is just this z-value when we use the tangent plane. So all we need to do to find the linearization is move that -3 over to the other side, and we're done. The linearization, this is going to approximate any value at x and y. It uses the tangent plane. It is going to be, I'm going to move that 3 over, 3 plus 1/3 times x minus 2 plus 1/6 times y minus 5. There's that linearization. So once we have the tangent plane, we have the linearization. And again, they are pretty much the exact same thing because the linearization uses the tangent plane to approximate a z-value. All right, so now let's do it. Let's approximate a z-value. So let's find approximately what the square root of 9.4 would be. So notice that if we didn't have calculators, this would be kind of it would be a little bit of a complicated process here to find the square root of 9.4. But we can easily do this by separating 9.4 into 2 times 2.1 plus 5.2. Now, notice that it is the same thing. If I multiply 2 times 2.1 and add 5.2, I get 9.4. And I did this because our original function is, let me write down the original function, it's square root of 2x plus y. And so I've sort of written it in a form where I can find a value for x I could plug in, and I could find a value for y that I could plug in for this number that I want to approximate. So I'm going to use the linear approximation here. So I'm going to use that linear approximation. I'm finding a z-value. It is going to be approximately 3 plus 1/3 times x. Sorry, the x value is, let me erase that, because we know the x value that we're looking for this at, that's 2.1. And x value 2.1, x value 2.1. Minus 2. I had to look back and see where I'm plugging this into. Don't forget we're plugging it all into here. Plus 1.6 times y. Now the y value that we can get from right here is 5.2 minus 5. All right, so this is 3 plus 2.1 minus 2 is 0.1 over 3 plus 5.2 minus 5, that's 0.2. 0.2 divided by 6, well, that's also 0.1 over 3. So this would be 3 plus 0.2, but you know what? I'm going to change it to a 2/30. So I'm going to move the decimal over in the numerator and denominator so I can not deal with decimal values anymore. 2/30 is the same as 1/15, and then if I get a common denominator, let's see, 3 times 15 is 45, I get 46/15. So that gives me an approximate value for the square root of 9.4. It's going to be approximately 46 divided by 15. Okay. So next, let's calculate the differential. Now the differential is the difference between the z-value at the initial point, which was 3. So it's the difference between 3 and whatever our approximate value will be. So in this case, we can even see what it would be right now, but I'm going to show you how to calculate it in a little bit of a different way. Right now, you can see that the difference between 3 and 46/15 is 1/15. We're going to calculate that in a different way. All right, so here's the formula for the differential. Differential can be calculated by finding the partial of f with respect to x and multiplying that by a change in x, plus partial with respect to y and multiplying that by a change in y. So here's another formula you should add in there, is that formula for the differential. Okay, so now to calculate that, so calculating our differential, it's going to be the partial of f with respect to x, we found that was 1/3, times our change in x. Now the change in x from our original to the point that we're looking for, that change is 0.1. Plus the partial with respect to y we found was 1/6, times that change, which goes from 5 to 5.2, that change is 0.2. And if you calculated this out, we actually did it even up above, you get 1/15. You get that difference between the initial z value, the z value from the point, and then the z value from the point that you're trying to now approximate it as. So notice that we have two different points going on here, an initial one and then an xy that we're actually trying to then find the approximation for. And the reason for this is that we find the tangent plane from a certain point. What we're looking for would be a point different from that. And if we can pick a point that is close, notice how 2.1 and 5.2 is close to 2.5, then we actually get a fairly accurate approximation. All right, one more thing to note, and that's finding tangent planes if we're given parametric equations. So tangent planes with parametric equations. What we're going to, or what I guess I'll give you kind of a formula for this. If you take the partial of the parametric equations, I'm going to do this in a vector form, with respect to one variable, and maybe I'll call that one x. No, I'll use the book notation u, plus the partial with respect to v. If we find that cross product, remember that a cross product of two vectors, and both of these vectors would now be on the tangent plane, because they would create the tangent plane from being the slope in one direction, say the x direction, and the slope in the other direction, say the y direction. If we cross them, we get a normal vector. Normal vector to the tangent plane. Okay, so here's an example. Let's just say that x is equal to u, y is equal to 2, and z is equal to u squared v. Let's find the tangent plane. Let's find the tangent plane at the point 1, -1, 1. So notice that I've given you 3 different points here, so really this does represent x, y, and z on here. If I gave you the point 1, -1, then it would probably represent uv. There'd be kind of a question in there. I would assume it would represent uv, but that may be then a poorly worded problem. But because there's 3 points, it's going to be an x, y, and a z. So what we need to do here is find a partial of all of these with respect to u. I'm going to put this in a vector form. So the vector is going to be 1, 0, and then this last one with respect to u is 2uv. Oops, vector form. Then the partial with respect to v, let's see, u is going to be a constant, so that derivative will be 0. 2 is a constant, so that's 0. And the last one, I get u squared. Now I'm going to cross them. I'm going to cross them. The x component, looks like that's going to be 0. The y component is going to be a negative u squared. And the z component is going to be 0. So now I need to figure out if this is an x, a y, and a z, then I need to figure out what u is so I can plug it in there. Now, let's see. Well, u is equal to x. That makes it pretty simple. So because u is equal to x, if x is equal to 1, well then of course u is going to equal 1. So this vector is going to be 0, negative 1, 0. That's going to be the normal vector to the tangent plane. And so I can plug that into our equation of the tangent plane with the normal vector. So there's a couple different ways that we could do this, I guess, depending on the formula that you like. But let's do this where we've got this first component 0 multiplied by x minus the x naught value, which is 1. The y value of the normal vector times y minus y naught. So that's going to be a y plus 1 because the y value is negative and we're subtracting it. Plus 0 times z minus that z naught value, which is 1. And we'll set that equal to 0. So if you simplify this, you're going to get, let's see, we'll get y equals negative 1, it looks like, right? Negative y minus 1, and bring it, yep. So there's our tangent plane. So pretty simple example here. The only thing that you really need to remember is if you're given parametric equations, the cross product of the derivatives is going to give you the normal vector.